Hi everyone, this is Josh Valentine with the Clean Coalition, and thanks for joining our webinar today. Today's webinar, The Neighborhood of the Future, an overview of the Alabama Smart Neighborhood Project. Our speaker today is Olu Ajala. He's a research engineer for the Research and Development Organization of Southern Company, a leading U.S. energy company. In this role, he is responsible for developing and managing a variety of projects within the renewables, storage, and distributed generation program area. This includes a portfolio of projects ranging from PV solar and wind energy systems to battery energy storage and microgrids. Before we get started, I'd like to point out some technical aspects of the webinar. The recording and the slides will be sent to all registered attendees within 2 business days, so you will have them by the end of the week. All of our webinars are archived on clean-coalition.org and on our YouTube channel. We will be having a question and answer session at the end of the webinar. If you have a question and you would like answered, please submit it in the questions box and you'll see that on your screen. It varies from operating system to operating system, so it may not look exactly like that, but that's where you should enter in your questions and we'll try to get to them at the end of the webinar. If you have any further questions about the Clean Coalition or the webinars, email me at josh@clean-coalition.org. Before we get to Olu, I'd like to introduce you to Rosanna Franciscato. She is a communications director for the Clean Coalition. She's going to go over a few things about our community microgrid work that the Clean Coalition does.
Great, thank you, Josh, and thank you everyone for joining us today. We are really excited about today's presentation, and that's not just because this is a state-of-the-art smart neighborhood, but also because it's one of the best examples in the country of what we're working on at the Clean Coalition, a community microgrid. And a community microgrid is a new way of designing and operating the electric grid. It's stacked with local renewables and staged for resilience. And community microgrids have all the features noted here: a targeted and coordinated distribution grid area, high penetrations of local renewables and other DER. And you can see that one of their features is that they can keep critical community facilities online indefinitely. So this benefits entire communities, not just one facility or one home. And this is very important, they can be replicated anywhere. So with all these features, community microgrids bring our communities unparalleled economic, environmental, and resilience benefits. The Clean Coalition's Community Microgrid Initiative has a goal of proliferating these deployments across the country. To that end, we're designing and staging community microgrids as showcases and models for what can be done anywhere. And you can see a lot of them listed here. That includes projects like our Goleta Load Pocket Community Microgrid in Southern California. Here in Northern California, we're working on a Calistoga Community Microgrid as part of our North Bay Community Resilience Initiative, and our Valencia Gardens Energy Storage Project listed here, and many more. These projects are really taking off now in response to wildfires and power shutoffs, which, as you may know, have become the new normal here in California. So in staging community microgrids like these in California and elsewhere, as we encounter obstacles in this work, we're identifying the policy and market mechanisms that are needed to unleash the microgrid market. Some of these are reform of the transmission access charges market distortion in California. This is adding 3 cents per kilowatt hour to the cost of clean local energy projects here. And that can be as much as 50% of their cost. So that's huge. Utility transmission divestment is also key. Divesting the utilities of their transmission assets would set the stage for them to become distribution system operators and support distributed energy. It's also essential that we streamline interconnection for commercial scale solar and storage, because right now that's irrationally costly and time consuming, and we can fix that. Effective procurement methods are also crucial, such as the state-of-the-art feed-in tariffs that we designed at the Clean Coalition. with market responsive pricing to make them cost effective, and dispatchability adders to incentivize energy storage. And we also need a standardized value of resilience for critical, priority, and discretionary loads. We call this VOR 123. This is important because while everyone understands the significant value of resilience, no one has yet put a dollar amount on that value, and that's holding back the market for community microgrids. So clearly this is a lot of work we need to do, and this is a lot of information. We will, as Josh mentioned, send out these slides after the webinar, and you can read more about this work at the links provided here. For now, it's important to note that because of market and policy obstacles like these, most community microgrids in the US aren't very far along yet. Now, that's certainly poised to change, and we're working toward that. But this is what makes the Alabama Smart Neighborhood Project so exciting. It's farther along than most of these projects, and it's been operational and fully inhabited for almost 2 years. So this project can show the way for others around the country, and it can teach us best practices as we move forward with community microgrids. So without further ado, I'd like to introduce our speaker for today, Olu Ajala, who will present on this groundbreaking project.
Hi, everyone. Thank you for that introduction. This is Olu Ajala, and I'm a senior research engineer with Southern Company, and I'm here to talk about the overview of the Alabama Power Smart Neighborhood Project. So just as a quick introduction, I'll start with the objective and then talk about the scope of the project. What exactly led to this smart neighborhood? So over the past few years, Alabama has been doing research, understanding customer needs, and because of the evolving customer expectations and future grid needs, Alabama Power decided to embark on this first-of-a-kind smart home community. And this project has three key aspects of the scope. The first part of the scope includes distributed energy resource, and basically tests different use cases looking at optimizing the cost, reliability, and environmental impact with a community-scale microgrid. The second part of the scope is demonstrating 62 high-performance homes with connected home technologies and providing an improved customer experience. And the third part of the project includes demonstrating buildings-to-grid integration to allow real-time interaction between the utility and individual customer, as well as between the utility and the microgrid. Now, to talk about this project, I'll basically give an overview of how this presentation is laid out. So I'll start with customer insights. What have we learned since this project has been built, and why some of the customers chose to live in this smart home? Next, I'll talk about the energy efficiency. Well, with each of the individual smart homes, there are high efficiency appliances, energy efficient appliances that are installed there. And I'll talk about those appliances and then talk about the impact of those appliances. Then I'll talk about the community scale microgrid. Community scale microgrid has different generation sources. I'll talk about the thought that went into designing the microgrid and also some of the lessons learned from the microgrid. And then I'll talk about transactive control, the different control schemes that is installed with the microgrid and the smart homes, and how they allow the interaction between the utility and individual homes, as well as between the utility and the microgrid. And finally, I'll just share different use cases and the lessons learned from those use cases. So to start with the customer insight, first I'll talk about the smart homes itself. So each of these smart homes, there are 62 of them. Each one of them have several circuits. And most important of all, it has controllable water heater and controllable HVAC unit. And as far as the high efficiency appliances, they're induction-based cooking stove, the high efficiency refrigerator, triple pane windows, and several other things that allow each of this home to essentially allow for load shedding. Now, looking at the HVAC, the high efficiency and the controllable HVAC unit and the controllable water heater, they can allow each individual homeowner to reduce costs on electricity and also allow the homeowner or allow the grid utilization or reduce demand on the grid. And by doing that, the only way to do that is for each of the HVAC and the water heater, they can basically do peak shaving. And during the peak hours of the day, try to preheat the water heater or preheat or pre-cool the HVAC unit outside of the peak hours. That'll reduce the cost during those peak hours and also reduce the demand during those hours. So that's just a summary on the smart homes. Now moving on to the customer insight, what we've learned from those who have moved into these homes. One thing that one would expect, starting with the whys and the who. The why is the external circle. If you see what I'm pointing at this point, the external circle talks about the why, and the internal circle talks about the who. One thing that one would expect with this smart neighborhood, with the microgrid and the smart homes, is that perhaps the smart tech and the microgrid might have been the biggest draw to the homes, but that is not the case. The biggest draw to the homes is the architecture, location, and community. That's based on all the 62 homeowners in this smart neighborhood. And then the next draw is about the smart tech that is included in each of the homes. But that constitutes about 34% of the homeowners. And then the energy efficient aspect, energy efficient construction, that constitutes about 12% of what drew the homeowners from choosing this home. And then the last is the microgrid. Microgrid, only 3% of the homeowners say the microgrid was the biggest draw to the home. Now looking at speaking of just the age demographic of those who occupy these homes, one will think that perhaps maybe age 20 to 30 or age 20 to 30 will be the majority, but that's not the case. The majority of the homeowners here is age 31 through 40. And then the next that constitutes about 35% is age 50 and above. And after that, age 41 to 50 constitutes about 15% of homeowners. And then age 20 to 30 constitutes about 12% of homeowners. So that summarizes our customer insight and just a survey that was conducted and to understand who are living in these homes and why they chose to come to these homes. Now, the next is the energy efficiency aspect of the smart homes. To paint a picture of how we assess the energy efficiency of these homes, we compare each one of the smart homes with a normalized square footage of an average Alabama home that uses all electric appliances. Here is an example of a normal Alabama home. Consumes about 1323 kilowatt hour. If we compare this to one of the smart homes with the smart appliances, the HVAC, the water heater, the ERV, the induction-based cooking stoves, you'll see that the average energy usage, the monthly average energy usage is reduced by 40%. That is a testament to how efficient the homes are built and the appliances that are used in the homes. Now, with some of the homes, there are electric vehicles. There's a Nissan Leaf and there's also a Model 3. Now, here's just to paint a picture of if from the smart homes, if electric vehicle is added, here's what happens to the energy consumption, the monthly average energy usage. From the smart home as the base, the energy consumption is increased by 27% with one electric vehicle. And then if a second electric vehicle is added, the energy consumption is increased to 47%. But one thing that you'll notice is at 57% increase from the base of the smart home, you'll see that the monthly consumption is about 1239 kilowatt hour. That is still less than the 1323 kilowatt hour consumption of an average Alabama home that doesn't have the smart appliances or not built to the energy efficiency level of that of the smart homes. So that's just a summary of the monthly energy consumption. Now, looking at the efficiency from a different perspective, pick a characteristic day in January 2019 to look at the energy profile throughout the day. In this case, you see the black line here shows the energy the average electric demand of the energy, the portfolio, the profile for this January 2019 day for an average Alabama home, which is the baseline. In comparison to the smart home, you'll see a reduced profile throughout the day. That is a testament to the smart appliances. And then compare this with one of the smart homes that has Model 3 electric vehicle, as a Tesla Model 3 electric vehicle. You can see that there's increased consumption later in the day. And then if we add the home that has a Nissan Leaf, you can see there's increased consumption early in the day and later in the day. This is a way for us to understand the consumption or the energy consumption habit of the consumers in order to figure out how to better serve the consumers. Now, to paint the picture of energy efficiency in one additional way, now we'll look at the advanced heat pump impacts of each of the home, of an average smart home versus an average Alabama home that use all electric appliances. Example, the winter demand example is January 30, 2019, while the summer demand is just characteristic day in August 2018. One thing you'll notice here, the blue line represents the baseline, the average Alabama home, while the red line represents the smart neighborhood home. As you can see here, around 7 a.m. in the morning, you'll see a reduction about 41% in energy demand because of the advanced heat pump used in a smart home. And looking at the summer demand, you'll see a reduction in energy demand of about 16%. So this is just to paint a picture of how efficiently built the home is and how efficient the advanced heat pump is. So that summarizes the energy efficiency. Now moving on to community scale microgrid. Before diving into the microgrid, I want to paint a picture of a lot of the thought that went into designing the microgrid, and then talk about the microgrid, what the design, and finally talk about the control aspect of the microgrid. So what is needed to make a microgrid successful? First, the functionality has to be defined. In this case, the key question to ask is, what should the microgrid be able to do? Should it be able to island successfully without a blackout? If there is a blackout, should the microgrid be able to black start the smart homes? Those are key questions to be answered in order to define the functionality. The next stage is to define generation capacity. Once the functionality has been defined, one has to understand what generation sources are needed and what are the sizes. For standard generator, what should be the size? And the power electronic resources, the PV, energy storage, fuel cell, what should the sizes be? And then after those have been answered, then the next stage is to talk about the coordinated control. There are multiple levels of control. What kind of devices and controls are needed? And then with those control devices, what kind of communication is required to support the optimization and device coordination? So those are three stages to look at in order to understand how to design the microgrid. Now, how did we design the microgrid? Looking at the functionality and then the capacity in this case. We have a 330 kilowatt solar PV array. We designed for energy storage that has 300 kilowatt with 682 kilowatt hour energy storage system, and a generator that has about 400 kilowatt standby and 360 kilowatt prime capacity. And for research purposes, we have 400 kilowatt load bank. So why did we design 330 kilowatt solar PV array? The key reason here is for the smart homes, the expected peak load is at about 250 to 300 kilowatts. So with 330 kilowatt solar array at peak, the solar should be able to carry the entire smart homes and export to the grid. And that's at peak. But the average consumption is about 50 to 70 kilowatts. So the solars during the day is typically carrying the entire load and then exporting to the grid. Now for the energy storage at 300 kilowatts with 682 kilowatt hour. It should be able to carry the load at peak for a little over 2 hours. But at average load, the energy storage should be able to carry the load for 4 to 5 hours. And with the backup generator, it should be able to carry the load at all times. So that basically summarizes the design, the functionality, and the capacity of our microgrid system. Now, looking at just a 1-year profile of the microgrid, the annual production is about 538,000 kilowatt hour. The annual smart neighborhood consumption is about 688,000 kilowatt hour. And the total amount of energy consumed at the smart homes by from the microgrid is 189,000 kilowatt hour. That's just 27% of the total. And I would explain why. During the time that the solar is generating power, which is during the day, most of the residents are out of the home at work. So the consumption is low at that point. But in the evening, when everyone is back home, solar is no longer generating, and energy storage compared to grid power, there's definitely going to be an element of optimization with the microgrid, but so the total generation from the microgrid, only 27% of the total enabled consumption is coming from the solar, because most of the generation from the solar is during the day when there are fewer residents at the homes, and then in the evening there's more consumption from the grid. So that explains the summary at the bottom there. Now, moving from the capacity and functionality, the next thing that one has to understand is the control. How should the microgrid be controlled, and in coordination with the different appliances in the smart homes? There are different layers of controls for the microgrid. The primary control, we're looking at the converter and generator system level controls and how they respond automatically to measurements. This is typically fast in nature. And the next one is the secondary control, where it works with the assets. The key thing here is to regulate the voltage and frequency, and this is typically slower in nature. So in regulating the voltage and frequency, what exactly are we looking to regulate? It's primarily the power quality. The power quality that the consumer sees. And to define the quality, I'll talk about the quality and talk about the power quality signature, and then explain what the customer really sees depending on the power quality signatures. In this case, what is power quality? It's essentially a measurement of the fitness of power delivered. And it's typically a voltage sine wave operating at 60 hertz for US electric grid. In other countries, it could be 50 hertz, but in this case, it's 60 hertz. There are many standards to support that are available to support and define the power quality. There's IEEE standards, IEC, National Fire Protection Association, NFPA, NEMA, and UL. Overall, when we talk about power quality, the magnitude of the voltage has to be regulated within a certain tolerance, and the frequency of the voltage has to be regulated within a certain tolerance. So why is it important? What do consumers see when we talk about power quality? Well, poor power quality impacts on consumers. It could cause premature failure in end-use devices, whether it's computers, relays, television, and light bulbs, capacitors inside electronic appliances, motors inside different equipment downstream, transformers and cables in between the power grid and the end-use equipment. With poor power quality, there could be premature failures, and there could be increased heating and losses, which will require more generation, but at a lower efficiency. So that is why power quality is important. What are power quality signatures? Well, for a good power quality delivered to end-use appliances, it's essentially a sine wave, and the frequency is uniform. So it has to be, it looks something like this normal here. Now, one example of bad power quality is when we have increased harmonics in the sine wave. What is an harmonic? Essentially a multiple of the base frequency being 60 hertz. harmonic, well, third harmonic will be around 180 hertz, and fifth harmonic will be around 300 hertz. So the point here is the sine wave is no longer, the wave is no longer pure sine wave. You see this fuzzy lines in the peak and the valley. What exactly do customers see when you're talking about harmonics introduced into the power quality? You will have increased heating and less efficient use of energy. So that's the impact to our customers. Looking at another power quality signature, when you have unbalanced load, you have different phases in a three-phase system. You have different magnitudes for each of the phase. When we're talking about a voltage sag occurs when the generation, when the load that is consuming power, it's beyond what the generation can handle. That's when we see a voltage sag. When we see a voltage swell is when the generation is much more than the load that's consuming power. So we see a voltage swell. All of this basically introduce inefficient use of energy. And then we have interruption where breaker opens, and then there's just because consumer sees in this case just no power. This is the power quality signature, and basically signifying there's lack of continuity in service. And then there's the frequency. So this frequency has to be regulated within a certain tolerance. But here's the signature of where you see frequency excursion. So power quality challenges in microgrid. So these are all things that needs to be considered in order to define the controller for the microgrid. In this case, there's on-grid and off-grid. While the microgrid is on-grid, this is what the microgrid should be focused on: voltage support. It has to control reactive power assets in order to support the demands of the load in the smart homes, controlling it will provide local support for the smart homes. And then it also has to support the grid for use cases such as demand reduction and local electricity cost reduction. So the microgrid has to be designed to use the different generation sources in order to reduce the cost of electricity locally. And finally, power quality issues can come from the grid, and the microgrid should be able to support the power quality locally. Now, when the microgrid or the smart homes is in island mode, that is, it's off-grid, disconnected from the grid, the microgrid, the primary function then is to form the grid, that is to control the voltage and control the frequency within the tolerance or required tolerance. And to control the frequency, the microgrid has to be able to provide real power to control frequency and should be able to provide reactive power in order to control the voltage. And furthermore, the microgrid has to be able to deal with system imbalance locally, and finally, power quality issues that are generated locally. So these are things that one needs to consider in designing the control system for the microgrid. Now, what can cause power quality issues within microgrids? Well, there are different potential causes. Transit conditions such as that of an islanding. If there's an unexpected trip upstream of the smart neighborhood, that will introduce transient conditions into the local system. Second is renewable generation due to transit changes in weather. For the solar, as we know, solar is very intermittent. Whenever there's cloud covering and so on, there's a drop in solar generation, and that can introduce transients into the local power system. Next, increased nonlinear loads or rectified loads. As part of the efficient appliances or the advanced heat pump is controlled by variable frequency drive, and that's a rectified load. That's a nonlinear load, and that includes that introduces transients into the system. And finally, increased loading on one phase over another during an island. With the smart neighborhood as it's built, different sections of those 62 homes are on individual phase. If there's increased loading in one phase versus the other, that also introduces power quality issues. So with all of that in mind, the different aspects of controls that one needs to be cognizant of All of that in mind, the program that we use to control the microgrid is called Seismic, and it takes into consideration all of those aspects. Seismic is a program it's an open source program being further developed by Oak Ridge National Lab. And what Seismic is tasked to do is to ensure that the generation assets in the microgrid can support multiple control modes while on grid, and while in island mode, it has to be able to form the grid, regulating the voltage and frequency. And furthermore, Seismic has to ensure that the energy storage system and generator can detect system issues and transition to grid forming controls seamlessly. And finally, the microgrid control can also coordinate islanding and resynchronization. So to do that, Seismic is pointing to different nodes throughout the microgrid, as the energy storage node, the PV node, generator node, and has to be able to conduct forecasting and get information from weather station, and use all of that into the algorithm that helps it effectively dispatch the microgrid efficiently and reliably. Now, the Seismic controller is used locally to control the microgrid, but then beyond the microgrid, the smart homes and the microgrid is connected to the distribution system. There has to be the right protection scheme to ensure that the microgrid can operate effectively. For grid-connected system and grid-connected events, overcurrent sensing is primarily used. But in the case of inverter-based system, when there's a fault, the current is usually low. So voltage sensing is introduced in order to help for islanded events. And these settings allow the microgrid to island safely and respond appropriately to grid events. Furthermore, the islanding recloser, well, there are two reclosers. In between the microgrid and the smart homes, there's a recloser, which are called the DER, Distributed Energy Resource Recloser. And then in between the smart homes and the main grid, there's the Power Control Center recloser. So the islanding recloser was adjusted to a more sensitive setting to island faster and improve rates of successful islanding events. Now, to talk about the transactive control aspect of this project, well, I've talked about Seismic already. Seismic is used to control the entire microgrid. For the microgrid, the different components have their own individual controller. The generator has a DICE controller. The solar PV has an SMA cluster controller. And the battery, we use a PowerSecure's algorithm on Siemens PLC. And all of that is being controlled by Seismic. Now, for the smart homes, there's a program developed by Pacific Northwest National Lab called Voltron, and that is used to control the water heater, the heat pump, and all the other sensors in the smart homes. Now, both Seismic and Voltron talk together in order to coordinate the operation of the microgrid and all the circuits in the smart homes, and also together they're able to create that transactive controls that allows interaction between the utility grid and individual homeowners, as well as between the utility grid and the microgrid. Now, after talking about all of those, about the capacity, functionality, and control, now moving on to the lessons learned so far on the different use cases with the microgrid. Some of the use cases that we've tested so far include the seamless automatic islanding, multi-source grid forming, protection schemes, voltage and power factor control at the Power Control Center, remote operations, PV smoothing, and transactive control. The first is looking at the power quality. For each of the phases going to the smart homes, there's a power quality analyzer, and there's one that's at the point of interconnection. The focus here will be on the power quality analyzer on the point of interconnection. The key point here is that we are measuring the power quality, primarily the power factor, in two scenarios. The first scenario is where the inverters are not set, or the microgrid is not set to control the power factor locally. And then the second scenario is where the inverters are set to control the power factor. When the inverters are not set to control the power factor, this is what the power factor looks like. The objective is for the power factor to be as close to unity as possible, and that is where the generation is being operated efficiently. But in this case, the power factor is erratic. And what is the cause of this erratic nature of the power factor? That's primarily cloud covering when solar is generating power, um, battery cycling, um, and also ramp up and ramp down of solar, sun rising or sunset. Those contribute to the erratic nature of the power factor. But when the inverters are set to control the power factor, this is what it looks like. You see that the power factor is either at 1 or -1. The 1 or -1 simply symbolizes the direction of power. It basically shows that either power is being generated or power is being absorbed. But the point here is that it's less erratic. It's more, the power factor is closer to unity when the inverters are set to control the power factor. And some of the things that the microgrid is doing here is, in the case of appliances consuming reactive power in the homes, there's a need for reactive power to normalize, to basically counterbalance the reactive power being, well, the inductive load. There's a need for capacitive VARs, reactive power, to counter the inductive loads in the homes. So it's either the reactive power is being provided by the grid or by the energy storage. So in this case, once the inverters are set and the microgrid is set to control the power factor, there's a chance where that the microgrid is providing VARs, reactive power, to ensure that the power factor is close to unity as possible. Next is an unintentional islanding event that was experienced this occurred third quarter 2018. So what happened here is that upstream of the smart homes, there was a fault that caused the power control center real power, that is the main recloser, to open. And as soon as that opened, the microgrid picked up the load immediately and ran and basically powered the smart homes for 30 minutes until the power control center operator resynchronized the smart homes. And here, the microgrid picked up the load and resynchronized with the grid seamlessly. The homeowners did not see any power blip. So to now go into the details of how this happened, well, I'll just explain what this chart in front of you depicts. The blue line is the power control center real power. That is the real power being provided by the grid. And then the red line is the energy storage real power. The black line is the photovoltaic, the solar real power. And the gray is the load real power. So what you see here is when the PCC real power dropped offline, that's when the main grid was disconnected. The solar dropped off as well, and that's because of the transient introduced by the drastic opening of the recloser. And once the solar dropped, the energy storage picked up the load. The red line, energy storage picked up the load immediately for the next 5 minutes before the solar came back online. And when the solar came back online, energy storage went into charging mode. Even though energy storage went into charging mode, it continued to form the grid. So energy storage was regulating the voltage and frequency. And that's because solar inverters cannot regulate frequency because of the intermittent nature of solar. So energy storage was forming the grid, solar was providing the power. And then over the next 30 minutes, when the power control center eventually resynchronized the grid, everything was seamless. And it went back to grid generation, solar exporting to the grid also generating power, and energy storage went back into its regular state. So this is an example of energy storage, the microgrid picking up the load and running the smart homes seamlessly without any interruption. Here's another example of an unintentional islanding that occurred. This occurred in October. So what happened here, October of this year, 2019. So what happened here, unlike the last example, is that the energy storage was not fully charged. That we just conducted maintenance on the energy storage, so it was at a lower state. Once the fault occurred upstream of the smart homes, energy storage tried to pick up the load initially, but the voltage was swinging back and forth, and as a result, the generator picked up the load. The generator took some time to start up. So, but when the generator eventually started up, it picked up the load, and generator and energy storage was operating simultaneously. But generator was primarily the grid former. So generator provided the voltage and frequency regulation throughout the 1 hour that the microgrid picked up the load, and then after that hour, the smart homes was resynchronized with the grid. So the difference here is that the prior islanding situation, energy storage and solar picked up the load for the 30 minutes during which the unintentional islanding occurred. But in this case, for the 1 hour, the generator had to pick up the load because the energy storage was not fully charged and was not capable of carrying the load for that period. So this is just to explain the multi-grid source forming capability of the microgrid. So in the first one, energy storage formed the grid. In this case, energy storage started to form the grid but couldn't, and then generator formed the grid. Here's the frequency. Here's the chart depicting the frequency during that second islanding event. What you see here is while the system was on grid, the frequency band was not as tight, but when the smart homes was islanded by the microgrid, the frequency band was much less. It was tighter. And after the hour, when the smart neighborhood was reconnected with the grid, the frequency band was wider again. Now, furthermore, I talked about harmonic introduction into the power quality signature. Here's an example. With the microgrid being an inverter-based system, the inverter introduces harmonic into the system as opposed to power from the grid. So in this case, this is depicting what the voltage looks like, the voltage signature. You might not see the harmonics clearly here on the voltage, but on the current, you can see the harmonics clearly. At the top, you see at the peak and the valleys, you see the harmonics clearly on the current. So this is just to depict the waveform distortion during the islanding situation. And then finally, voltage imbalance. Here, voltage imbalance at the microgrid is consistent throughout the day at approximately 0.005 per unit voltage, while on the load side, the load imbalance is inconsistent throughout the day, but it's somewhat balanced among the phases. So overall, I've talked about the microgrid, what went into designing the microgrid, talked about the smart homes, customer insight. Now, what we've done with the microgrid so far is we've done, for the different use cases on the microgrid, we've done PV smoothing to help smoothing the ramp up and ramp down and reduce the impact on the power factor. We've done economic dispatch using arbitrary cost to try to optimize the dispatch of the microgrid. We've talked about power factor control and also talked about different cases of islanding and how the microgrid was able to carry the smart homes in different cases of islanding, which also includes the multi-source grid forming. And next steps, we're looking to dispatch the home loads and essentially creating virtual power plants in a way, because the smart home appliances, there'll be some load shifting, especially for the HVAC and water heater. And then on the microgrid side, looking at ways to to use the energy storage in order to provide benefits to the grid. Next, we're looking at testing long-term islanding capabilities of the microgrid. We have solar, we have energy storage, and backup gas generator. Objective here is to see how long we can have the microgrid carry the load without power from the grid. And finally, transition into a permanent control system. Seismic is being developed by ORNL, but we're looking to transition to a more permanent system or commercial system in the future. So that summarizes the Smart Neighborhood Project. Overall, talked about the key objective of this smart neighborhood is where Alabama Power wants to understand more of the customer, the consumer trends, and design this smart neighborhood to test the technical feasibility of smart homes with smart appliances and a microgrid, so that we can understand the benefit it can have for the customers and also the benefit for the utility grid. And we want to continue to do this test and get as much information as possible to inform future decisions or future decisions about smart neighborhood and neighborhood of the future. And I would like to thank everyone for listening and hand over back to Josh to open the floor for questions.
Thank you so much, Olu. Great presentation. If you could just keep that screen, that slide where it is, that would be great. And we've got a bunch of questions here. We'll try to get to some of them. And I apologize in advance if we don't get to your question. But we've got a good 12 minutes left, so we can get to a good amount. So Olu, I'm going to ask these two questions. If you ever need me to repeat anything, just let me know. These questions are sort of related. Were asked by Carol Steinfeld of Ecovita and Isaac Mays-Rothstein at Wood Mackenzie. How much were and are these homes, and what was the range of the cost of these homes? Well, that's basically the same question. Were the age demographics related to the size and cost of the homes, and how was the overall project financed?
So with questions about the cost of the homes, my colleague who was in charge of the home aspect of things, my primary focus is on the microgrid, but I can get the information of the person that asked that question, and I can follow up with you with that information.
Okay, great, thanks. All right, again, we've got some questions that are from Hugh Kuhn and then Isaac Mays-Rothstein again. They asked, there's no mention of residential solar within the project. It seems odd given the opportunity to design the homes to optimize local generation as well. And then Isaac goes on to ask, there is no solar or storage on the homes, correct? If so, how is the wiring done between the central microgrid system?
So, well, the central microgrid system is located about half a mile from the smart homes, and the objective of this project is to test more of a central microgrid as opposed to having local solar plus storage in each home. We have another project in Atlanta that actually has local solar and storage in each home, so that's a separate project.
Okay, thank you. And Martin Hersfeld from IREC, who's with an IREC certified master trainer for PV installation. Martin asks, is there a possible solution for not using natural gas at all?
There could be a solution. It just depends on and that's why the functionality, defining the functionality is important. In this case, if you do not want, well, we wanted to be able to island the smart homes indefinitely. We know the size of the smart homes on normal operation of 50 to 70 kilowatts, and then at peak about 250 to 300. If you want to design energy storage to be able to handle that load for 2 days, 3 days, that would determine the size of your energy storage. So if in this case we designed it just to be able to operate the peak for 2 hours and then normal operation for 4 to 5 hours, but then the gas backup generator can carry the load indefinitely for as long as we have gas supply. So for one to design a system that doesn't have a generator backup, then you have to size your energy storage for the duration that you require.
Thanks a lot. Okay, so Nathaniel Iltis is an energy engineer at Beyond Efficiency Incorporated. Nathaniel is asking, what is a black start of a home and why does it matter?
So black start of a home, well, if the main grid is disconnected and in a situation where the microgrid did not pick up the load before initially, then you have to be able to black start the community from no power, and that is why we wanted to test that use case to ensure that this microgrid is able to coordinate that load and effect the black start.
Great, thank you. Robert Perry from the World Business Academy and Hugh Kuhn are asking some questions that are related. Are the houses all wired for EVs, and do any residents work at home with higher load and EV charging in the afternoon? I would think that would yield high benefits. Are EVs able to discharge to the home during outages?
Well, in this case, we haven't tested the EV discharge into the homes, but the homes are wired for EVs, and there are 2 of the homeowners that have EVs.
Great, and in continuation on that topic, Hugh Kuhn asks, why would the Leaf and Model 3 consumption patterns be different? Was there any attempt to charge the EVs at specific hours?
Well, it's basically how the homeowners are using their EVs. So all we were doing was just measuring the profile based on how the homeowner is using the EVs. That's not being controlled by Alabama Power.
Okay, thank you. All right, so Bill Hilton is a volunteer with the California Interfaith Power and Light organization. Bill is asking, what is a controllable water heater? Is it a heat pump? Is it for resistance or another fuel?
Heat pump, advanced heat pump.
Very good.
So what we're doing is just being able to, the objective there and what we're testing is when homeowners are looking to use hot water, the objective is to be able to preheat the hot water away from the peak period in order to help the homeowners save cost of electricity during the peak and also to reduce the demand during the peak. So that's our objective with the controllable water heater. But to answer your question, it is advanced heat pump.
Great, thank you. Robert Perry from World Business Academy is asking, is the energy storage able to soak up excess energy in the afternoon? And how often is excess transmitted to the grid? Have scenarios been run with larger energy storage or an electrolyzer component?
Well, the energy storage size that we have there is 300 kilowatts with 682 kilowatt hours. That's just the size of the Samsung energy storage system that we have there. And yes, it can take energy from the grid, and it can also take energy from the solar from the PV array out there. We've test situations where we give a price signal to see how the microgrid can optimize generation. So the microgrid will look at charging and discharging of the energy storage in order to optimize the price per the arbitrary price signal that we have there. So does that answer your question about optimizing the energy storage?
What was that? Were you trying to clarify something, or were you done with your thought? Sorry about that.
So the point there is just there's the energy storage is there. It's a fixed size. We're not changing the size of the energy storage. It's a fixed size. And to the question about if the energy storage can store energy, yes. To expound on that, energy storage can store energy from the solar array, and in the situation where we put in an arbitrary price to have the microgrid optimized generation, it basically stores energy from the solar. The solar is excessive. It powers the entire smart homes. Energy storage can store energy, and the solar also exports to the grid.
Excellent, thank you. Well, we have a question from Gregory Young, who was with the Clean Coalition. Gregory is asking, in the case where the generator was required due to lack of energy in the battery, could the generator simply have charged the battery to full along with all the other real-time loads and then been shut off to run from the battery again?
Well, if we have no power from the grid, that would be what could happen. But in this case, if we have access to power from the grid, we will definitely not want the generator to charge the battery because that would be a lot more expensive.
Great. Erica Van Dyke is asking, what were the largest cost savings for the utility from the microgrid? Is it T&D deferral, energy price arbitrage, etc.?
So the purpose of this project was more of research, and this project is definitely not economical. The primary purpose is research, and all we're doing is trying to understand the technical feasibility of a microgrid.
All right, and Robert Perry, again from World Business Academy, is asking, can lessons learned be applied to high-density multifamily developments?
Yes, well, absolutely, because in this case, as I showed, the different high efficiency appliances, the smart technology, and the way those appliances were able to reduce energy demand, as I showed earlier, about 40% reduction in energy demand. That is something that could be applied to multifamily development by installing high efficiency appliances and installing well, in general, appliances that can help reduce the demand for electricity. And for the microgrid, at this point, it is not quite economical, especially not here in the southeast. And one can, and that in itself is a lesson for other developers of, multifamily homes and microgrids in general. So yes, there is lessons learned that can be applied.
Great, thank you. Tristan de Franville, CEO of Skycentrics, as asking, why are you not going to use seismic in the future? You mentioned moving to a commercial system. Is it because seismic is not good enough?
Well, I mean, seismic has allowed us to be able to test different extremes of the smart homes and microgrid. However, it's not fully commercial yet. And moving forward, we're looking to install a commercial system. That is the key reason.
Great. Isaac Mays Rothstein from Wood Mackenzie is asking, what have been your biggest surprises through your current tests and blackout events?
What has been our biggest surprises in our tests? Well, the biggest surprise is we're testing long duration islanding. We haven't been able to achieve 1 week of long duration islanding, but we continue to test it. We just testing with the load bank, not with the smart homes. We've been able to achieve 2.5 days of islanding, and that 2.5 days of islanding is actually good when looking at the different kind of the complicated nature of this microgrid, where different generation sources forms the grid, and there's interchange between the different generation sources while the smart homes or while the microgrid is islanded. So that complicated nature is something that we're still working on to try to figure out how to get it right, but we continue to test it. So that is the biggest surprise. one will expect, with the control system that we have with the microgrid and generation sources, that it should be easy to just go ahead and to execute long duration islanding. But at this point, we're still trying to get that right.
Excellent. So we have time for, I think I'll ask two more. We have time for two more. William Buchan, the CEO of Market Potential Incorporated, is asking, in the microgrid, are you able to transmit energy data in a real-time fashion? If so, how? If not, would this be advantageous?
Are we able to transform? Could you repeat the question?
Sure. In the microgrid, are you able to transmit energy data in real-time fashion?
Well, I mean, we have remote operation, and we are getting, there's an HMI local to the microgrid that we can use to measure different points in the microgrid, and we have remote operation as well, where we are getting information from the microgrid.
Great, thank you. All right, so why don't we close out with this question from John Supp. He's an account service manager with Silicon Valley Clean Energy. John is asking, how much of the barrier for islanding is technical? In other words, storage capacity, replenishment rate, etc., versus behavioral / lifestyle.
Let me try to understand that question better. How much? Could you repeat the question?
Yeah, I think what John is asking he's asking what the barrier for islanding is, if technical versus behavioral or lifestyle. So he mentions that over 180,000 homes are off grid. So why can't others be off grid? If it's purely a matter of behavioral lifestyle for barrier for islanding.
Did you say over 180,000 homes are off grid?
Well, that's what John mentioned, but in terms of trying to put the question in context, yeah.
Well, let me try to answer that question. Well, when we're talking about off-grid, just to make sure that I understand the question, is that question about why can't the entire system be off-grid? I'm trying to understand.
I think he's saying well, I think he's asking why others can't be. I think that's the
why
gist.
Others can be off-grid?
Yeah.
Well, I mean, in this particular project, we are testing the technical feasibility of microgrid, and we definitely understand that it's not economical, but we just want to understand what kind of benefit can we get from it from a technical standpoint. And there's a lot of research, a lot of theoretical research around microgrid and its benefit, and our objective here is to get empirical data to understand those technical benefits, but it's not economical. So I guess a barrier for it not being everywhere is definitely economics.
Excellent. Well, thank you, Olu. That about wraps up the Q&A session. So we went a bit over, but I'm glad we got a bunch of those in. So again, I would like to thank you very much on behalf of the Clean Coalition for presenting for us, and for those who are interested in forwarding this webinar and the slides, we will be sending those out in the next couple of days, and then we'll be putting those on our website as well. So we're going to have another webinar in the end of January, so look out for information about that. And thank you again, Olu.
Thank you very much, Josh.
All right, you have a good day. Have a good day. Have a great day, everybody.